I hurt my back, and so I'm like hurting. And I was told I have lots of slides, so I'll talk fast. So anyway, let's jump into it. I want to acknowledge all the PIs, co-PIs, and the students that work on this project. There have also been others. And let's talk about rural roads. A lot of people unfortunately die on rural roads. 43% of all fatalities are on rural roads. Rural roads have twice the crashes per VM, I'm sorry, fatalities per VMT than urban roads. And there's a lot of challenges in rural areas. We got issues with, well, we got vast network, we got animals, we got pedestrians, we got medical facilities that are not very close, and first responders are not very close. So we're trying to build a system to make rural roads safer. That's what it's all about, right? And this is James made this architecture. Now this is kind of kind of our guidance here. And what I'm going to be talking about now is curves, pedestrians, animals. Let's start with curves. Well, previous studies have shown that crashes are more prevalent on curves. Fatal crashes, crash severity is much higher on curves. And single vehicle crashes are like the most prevalent type of crashes on curves. Now, primary contributing factor is driving too fast. So we want to slow people down when they approach curves. How do we do that? With some sort of warning system, okay? So this warning system that we've been trying to develop, it requires a lot of data and vast specialized data. And so to create this data, well, let's first talk about one of my favorite movies of all time, The Martian. You've seen The Martian? Okay. There's a new movie out right now, Hail Mary, by the same author. Okay. And so let's see if this video works. This is an excerpt.
In the face of overwhelming odds, I'm the only one. I science the shit.
Okay, I won't repeat that. Okay, I will. It's in the face of overwhelming odds. He's like stranded on Mars, right? So to come home safe, he's going to have to science the shit out of this, right? So how does that relate to this? Well, to get the data we need, we're going to have to we're going to have to GIS the shit out of this. So let's talk about curve advisory speeds. Well, there's lots of methods to collect curve advisory speeds. But I want to talk about the AASHTO one. That is the most that's the most prevalent deterministic way to do it. Okay, and actually for this project, I like it because F we can cater. I'll come back to that. Okay, but what we're trying to do is solve for design speed, which is a surrogate for advisory speed. Right? If we have radius, banking of the curve, and this F. Okay, so first thing we need is radius. How are we going to get it? Okay. What was it again? GIS out of this? Yeah. So here we can use, okay, if you know about GIS does not store curve information or I'm sorry, it's not like CAD where you can have an arc that has a radius. It stores shape points. So what we need to do is pull out from those shape points radii, right? And so that's what we did. And what we have here is a whole series of curves that fall out of the GIS. But we don't need all of them, at least not for advisory curves, because many of them have radius that are very large. So we can filter those out, right? And they're gone. Okay, then we have some issues though, because as it turns out, this algorithm actually generates sometimes a lot of compound curves. In reality, those curves are supposed to be fixed radii curve. So Farhad, who just walked in late into my presentation, he basically came up with some cool Python scripts that we used high school students that were graduating to go and fix our data, right? And so we go from what we have on the left to things on the right with these Python scripts that Farhad has used. And I'm gonna mention his name a lot because basically he was the brains behind this. I just tell him what to do. And so yeah, here's the example. All right, we got radius. All right, and we're going to put a little edge computing device. We'll come back to that, right? But what we also need is the banking of the road, because the banking of the road resists that flying around off the curve sort of thing, right? And so how are we going to get super elevation cheaply, right? Well, actually, as it turns out, all states have aerial LiDAR. South Carolina has it also. So what we can do is just pull off, banking of the road from it, right? It's not that easy though, because you see, we have some roads. Can't see the roads. Why? Because we have trees. All right. So, we Farhad thought about it. As okay, so Farhad, do me a favor, buffer the curve. Okay. Then go to the middle of the curve someplace, all right? Because again, the curve's transitioning. So we don't want to be down here or down up here, because that's not full super. We want full super. Then in this little buffer area here, okay, get rid of the trees. And so Farhad came up with this ransack algorithm that's kind of robust to outliers, so he's able to filter it out. And now we got, hey, super elevation, and we actually have grade too. And we're giving this back to like the South Carolina Department of Education. All right, and then how do we know it's good? I put the students in harm's way. Well, I took the pictures. And so we used, digital levels, auto level and such, and we're within 1%. And, from a sensitivity analysis, 1% is not going to affect advisory speeds very much. So we're good. We're good. So now we got what we need. Oh, don't forget the friction coefficient. Well, those of you who took highway design, you can, based on your postal speed limit, we can get a friction coefficient. But it's conservative. It assumes wet pavements, like so 0.1. We can actually do better with dry pavement, right? So with James here, getting scene, recognizing the scene and scene understanding, we can pull out and do better friction coefficients that cater to the curves at that time. Plus, we can consider the vehicle as well. And then here's our curve warning system. Okay, and so yeah, it's kind of a mess. All right, but we also added, okay, so it has a coded device, a communication device, we use the GPS from that. We have a camera, so we see the curve, so we can verify what we're doing here, okay? And then let's just jump into it. Okay, so here we are. I am speeding, okay, on purpose, because we gotta make sure it works, right? And so I am putting myself in harm's way. But that's okay, Farhad was in the car too. And so we're traveling at 52 miles per hour. The advisory speed calculated is 42, and the speed limit is 35. So I'm definitely speeding, okay? But we're only about 10 miles per hour above. So that's not too bad, right? So that's our yellow alert condition. And here, this is the warning here where it goes, yellow, and that's what's going to be warning the driver, that part. The stuff on the right, all that fine print, that's for us, the data. It shows like what the next curve is. It shows, the radius, the super elevation data, everything, right? Okay, well, what if you have a situation where you're driving way faster? Okay, so here I am, 51 miles per hour, and the advisory speed calculated is 32, right? In that case, we're going to die, right? So that's like our red alert condition. And so it will change its warning. Red alert, it can audio, slow down or die, right? And so yeah. And anyway, so there you go. So that's, and it also though, it'll tell you what the next curve is and where you're turning. Okay. The next warning system, the deer warning system. All right. Well, deer collisions are bad. 440 fatalities a year. How many fatalities do we have in the United States every year? About 40,000. So this is more than 1%. This is very significant, right? And deer is a major problem, right? And so our idea is, hey, let's warn drivers of deer. And what that will do is, what's our perception reaction time we use for design? 2.5 seconds, right? But if you are alert, like traffic signals, we say like one second, basically, watching yellow, that's what we're trying to do, make a driver more alert, right? So if they can be told, hey, deer in the area, right? Well, then maybe their senses will be in such that, hey, I'm alerted, right? I can lower that perception reaction time down, and then maybe react to the deer much better. So that's what we're trying to do, is warn the driver of deer. Well, deer come out at night, though. Okay, they're hard to see until the very last second. They freeze, they're stupid. Okay, they freeze until you get really close and they say, oh, I gotta run now. And that's when you hit the deer, right? So what we want to do though is make them more visible at night. And so we decided to use a thermal camera. So I bought, of course I didn't have a lot of budget, I bought the cheapest thermal camera that we get, okay? But it still worked pretty darn good. We mounted it to the windshield wiper, right? And the great thing about it is it doesn't matter if it's night or day, you see the same thing, right? Fog, you see the same thing, right? And so it was work. So, but then we needed, as it turns out, some of this data that comes with like YOLO, these computer vision sensors, They have, like, some animals, no thermal data. So we had the deer hunting. So that's what we did. We went to North Carolina and we actually collected about 30,000 images of deer. And so that's, and here's some video. And you see there's actually 3 deer. Can you see 3?
Yeah.
There's 1, there's 2. Oh, there it is. There's the 3rd one. See, they're tough to see in the bushes, right? And we need, though, that training imagery that shows occlusions of deer. Because deer don't just stand out right in front of you. They are kind of hidden, so we got to be able to train. All right, so now we got 30,000, and then we pulled out some of the redundancy, so we're down to 12,000, and then we had students annotate, right? And so then we ended up with about 9,000 for training, about 3,000 for validation and testing. Right, and here's our confusion matrix here. It kind of shows the results here where we have, okay, so right here it says, hey, true positive, right? Okay, false positive. In other words, it senses a deer and there's not a deer. But that's not nearly as bad as this, not sensing a deer when there is a deer, right? So if we warn a driver and there's not a deer, not a big deal. You can cry wolf, so we got to be careful about that. But that's not nearly as important as this right here, and we don't have a lot of that. So the training, hey, this system looks good. Okay, we went out and verified, and it is blowing. It works. I didn't touch it. Okay, it works. It works pretty well. Okay, remember now, it's only seeing part of the deer, so it's not jumping up to 98% probability right away, until you get more of the deer. Okay, but even with that lower probability, all we're doing is warning the driver, right? That there's a possibility there, right? And then as you get closer, okay, then the probability goes up, right? When the probability reaches a certain level, that's what we broadcast and say to other OBUs, to other roadside units that broadcast and pass on the information. So as cars approach, okay, those areas until the message expires or it's continued, okay, then again we'll warn people of deer. Okay. The problem with these thermal cameras is the resolution is not the best. Okay, not nearly as good as regular cameras. But mine was cheap, like I said, as we get into better cameras, we'll have better resolution because the thermal cameras can see a long ways. It's just the resolution is the problem, right? Okay, and so here, all right, well, unfortunately, we don't have deer in Clemson. It's tough to find deer in Clemson. So we did a little with pedestrians in Clemson to get our communication system working. Next month, we are going back up to North Carolina with a whole integrated system to test it, okay? But the pedestrians, it works. This thing finds a pedestrian, and all of a sudden it's gonna say that, hey, there's a pedestrian. And this OBU identifies the pedestrian, but it also broadcasts it to other OBUs and roadside units. And so we get the message that, okay, so in this scenario, it says that, oh, okay, this is OBU2, but it says OBU1, okay, found a pedestrian, so we alert OBU2. The driver doesn't get the message though until it gets close, okay? You don't want to, until they get close, right? And so that's what happens. And then also, here's our roadside unit. Okay, so our rock is sitting on the side of the thing. It's gonna look more like this, but this is how it works. And again, what does it do? It's it's saying, oh hey, there's a pedestrian, which would be the deer or the whatever it is, detected by OB1. By the way, pedestrians in rural roads, they're bad too. Okay, so it's still a good thing to sense it. Okay, that's all I got. It's on you.
Thank you. Very good, exciting presentation. So this is just a part of the part to that one. So basically major planet engaging. We here just deploy the AI model foundation field on edge. So here. So basically we try to leverage the generative AI, right, technology to perceive the environment condition or become a condition awareness detection. So basically, we feel a much model tool that can be deployed on edge from the larger model. So the major task here to do is to identify weather condition, which means real weather condition at a local one, and also the pavement widening level from the visual or from the other thinking model as well for information. And there are some kind of special objects in action as well, including the deer is one of them. We also detect other animals as well. And traffic condition as well, right? If you have something happen, then traffic will be from stop and go. Congestion, those kind of conditions are also going to be up by the model. So if we have got very comprehensive understanding of the environment, rural environment, the PV and EV vehicle driving on that. Basically, everything deployed on a roadside unit where we have to be strategically, keep that location, right? Where we have to present. And then that all communicating with connecting vehicle off the vehicle, on board in. So using we track, technology. And basically the one that thing here, I just show you here, given that thing there, we try to kind of perceive what that means, right? In terms of weather, condition, and traffic. And what we did is we kind of average a multi-agent framework to distill knowledge. Let's say we got one agent, not agent one. Basically, one of the I think we use ChatGPT, I think that's GPT for 1.5, which I remember correctly. So and with that model, the large language model to generating the equation, right? And then with that information, supervise the model to kind of handle that and figure it out. So we also have another agent called reasoning, right? So it's not only to describe what's happening, but also reasoning what potential risk will be based on that. Okay. So we got perception reasoning to come together. So we train a model to do both. So that's that. And here kind of some result regarding the weather thing understanding. So we did a different prompting, chain of thought prompting, and using multimodal data compared with the chain of thought prompting with just video data. So you can see, the great improvement with the multimodal data improved. And this traffic thing understanding, so we have flavor published on the report. So link there, if you're interested, you can read that often. And the conclusion here will be, I think way you want to know. Okay. Yeah. We have curve warning system has potential, right? To use, their price, by that and give her a long warning, both from the roadside unit and also the onboard unit, right? Because we communicate to each other. And we try to target in the deep learning consideration thinking and multimodal thinking, leveraging, the foundation model, for edge computing to give you much richer, comprehensive, weather perception detection. And in this summer, this project is roughly 8% complete at this moment. So we could spend summer to do the big testing as a study. Basically, we have to integrate work from different groups together to make it a fully functional system. So that's our work this summer. With that, which is I think we'll proceed with before we proceed another one that give a round of applause for